Welcome back, students. I am Sudipto Karmakar, Assistant Professor of Physics, SVIST, and in today's class we will discuss a question that came in MAKAUT in the year 2024-25 odd semester. This question is from the topic quantum mechanics, and it says a particle trapped in an infinite one-dimensional potential well of width L. Write its wave function and probability density function in its excited state, and also find the probability density at x equals to L by 2. So let's start. We know in case of one-dimensional infinite potential well, if this is the infinite potential well extending from x equals to 0 to x equals to L, then the particle that is trapped within it, its corresponding wave function will be defined as the wave function for the particle trapped in one-dimensional potential well of width L. It is given by psi of x, that is the wave function. We denote the wave function by psi of x. It is equals to root under 2 by L. Now what is L? L is the extension or width of the potential well. Okay, into sine n pi x by L. Now what is N? N is the quantum state or state number of the particle. So it is the wave function for any particle that is trapped within one-dimensional potential well of width L. Now what about its ground state wave function? So for ground state, n equals to 1. So ground state wave function is defined as, since it is depending on n, so I am adding a suffix n here. So the ground state wave function, that is for n equals to 1, it is given by psi 1 x, that is equals to root over 2 by L sine. If I substitute n equals to 1 over here, then we get sine pi x by L. So it is our ground state wave function. In the question, it is asked that write its wave function and probability density function in its excited state. So I am considering here the first excited state. So for first excited state, that is for n equals to 2, the corresponding wave function is given by, we just have to substitute n equals to 2 over in this expression. So we get psi 2x, that is equals to root under 2 by L sine. If I substitute here n equals to 2, then we get sine 2 pi x by L. So this is the wave function of the particle in its first excited state, which is trapped within one-dimensional infinite potential well. So the first part is complete of the question. So now we have to evaluate the probability density of the particle in its excited state. So probability density it is denoted by, or it is represented by rho, that is mod of psi x squared. So the probability density is mod of root under 2 by L sine 2 pi x by L square. Here we have assumed that the particle in its first excited state, so I have just substituted the wave function for this first excited state. Okay. So it results 2 by L sine square 2 pi x by L. So it is the probability density of the particle. Okay. So this is the probability density of the particle. Now what about the probability of finding the particle within the range L by 2? As you can see in the question that the probability density of the function in its first excited state, find the probability density at x equals to L by 2. Now I am here just trying to evaluate the probability. Okay. So the total probability of finding the particle within up to L by 2 distance, that is the probability of finding the particle from 0 to x equals to L by 2. The probability is given by integral, here P stands for the probability, okay, integral from x equals to 0 to x equals to L by 2, right? Mod psi 2x square dx. That results mod psi 2x square, that means 2 by L sine square 2 pi x by L. So here we have from 0 to L by 2, 2 by L sine square 2 pi x by L dx. Okay, so we just need to evaluate this integral. 2 by L is a constant, so I am taking it just outside of the integral sign. So integral, that is from 0 to L by 2 sine square 2 pi x by L dx. Okay. So now we have to evaluate this integral. This gives us 1 by L integral 0 to L by 2 2 sine square 2 pi x by L dx. And we all know a formula that cos 2 theta, that is equals to 1 minus 2 sine square theta, right? So 2 sine square theta can also be written as 1 minus cos 2 theta. So I am just using this formula over here. So 2 sine square 2 pi x by L can also be written as 1 minus the role 2 theta is here played by the role theta is played by 2 pi x by L. So here we can write 1 minus cos 4 pi x by L dx. Okay. Now it is a general integral that is easy to solve. So outside of the integral sign we have 1 by L. Within the third bracket we have integral from 0 to L. Sorry, it's L by 2. L by 2 dx minus integral from 0 to L by 2 cos 4 pi x by L dx. Okay. That gives us the first integral is x with the limit from 0 to L minus, it results L by 4 pi, it is a constant, and the integral of cos, that results sine 4 pi x by L, limit from 0 to L by 2. Okay. Now, what will be the simplified value? It results 1 by L. Within third bracket we have L by 2 minus 0 minus L by 4, and as we put here the upper limit, that means for sine 4 pi L, I am substituting here at the position of x L by 2, that is L by 2, minus, if we put x equal to 0, so it simply becomes 0, the total argument under sine. Okay. So it gives us L by 2 minus L by 4 pi, and as you can see that L cancels out, this 2 and 4 cancels out, results sine 2 pi minus sine 0, and sine 2 pi is 0 and also sine 0 is also 0, so that means this term goes to 0 and also this term goes to 0, so this total second term vanishes. That results only 1 by L into L by 2. Okay, so this L and cancels out. As a result, I have 1 by 2. So the probability of finding the particle at the position L by 2 is half. This is the answer of the question. Thank you. See you in the next video.